Hello, my name is Joshua Tyler, and I'm once again back, and I'm here to do some more MATLAB Cody work to kind of help onboard people into how to use MATLAB, and kind of go through that, go through my thought process because I do research that's accelerated doing MATLAB, so I use it on a pretty high functioning level. So I want to help share these best practices that I've come up with, also seen on the Mathworks help and examples. So let's get back to it. I think I finished number 12, problem 12 last time, which was solving the Fibonacci sequence. So here we're going to go to problem 13, remove all the constants. Okay, so essentially we parse whatever character this is and remove anything that might be a consonant. Okay, so we have our input. Let's just say our input here is Jack and Jill went up the hill. Okay, so what I would do is I would start a counter, an iterant. So I'll say C here for our counter. And then our character should have some length, and we can find that by saying for I equals 1 to length of our character string S1. Let's see. We'll say if the sum of S1 of I is equal to, let's just go ahead and label out all the consonants. So B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X. And we'll go ahead and say Y is a consonant here. And then we'll do the same thing in capital letters: B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, U, V, W, X, Y, Z. Say that is equal to 0. Then we'll create a new character. So we'll say output S2 of I equals S1 of I. And then counter equals, actually, we'll say counter equal, and then we'll say counter equals counter plus 1. I think in C it's just counter plus plus, but that's not how MATLAB works. Okay, so let's run this function. Unrecognized function S1. Why not S1? Wait, S1. Oh, that's right. So sometimes I say C, sometimes I don't. Okay, there we go. Initialize it as 1. Okay, so that should be what that is. A-A-I-E-U-E-I. A-A-I-E-U-E-I. Okay, so let's submit that and see how Cody likes it. All right, looks like they like that. So we'll go to number 14. We'll say find the numeric mean of prime numbers in a matrix. Okay, so input is 8, 3, 5, and 9. Output is 4, or 3 plus 5 divided by 2. Okay, so essentially we want to see if the numbers are prime. So I'm going to open up my MATLAB here, and I'll say problem 14, find the numeric mean of, what's it, all values, the prime numbers in a matrix. Prime in matrix. All CLC. Clear all CLC. Okay. Um, okay, so let's say x equals a random integer with size. Size mn equals rand I. Size mn size mn. Let's give it a range. It can be a 2 by 2 up to a 5 by 5. And then let's give it 1 to 100 can be the values in there. Random positive integer. Okay. So I think, was there x is prime x? Okay, that makes it a lot easier. Okay, so then we'll say prime numbers equals is x of is prime x, which makes that a lot easier. And then we'll say output equals some prime numbers divided by length prime numbers. Okay, so here we get 71, 5, and 83 as prime numbers. I believe that's right. I know 5 is. I know 70 is divisible by what? 10, 7, 5, 2. 71 is divisible by 12, I believe. And all the numbers that come with that. It's not divisible by 36. Yes, it is divisible by 36. So it's divided by, what is it? 3 times 2 times 2 times 3 times 2. Wait, 3 times 2 times 3 times 2. So 3 squared times 2 squared. 3 times 3 times 2 times 2, 36. Okay, so it's 3 squared times 2 squared. 3 cubed times 2 squared. Or no. No, it's 3 squared times 2 cubed, which is 72. So it's funny that 70 has a lot of numbers in it. And then 70 is highly divisible, and then 72 is highly divisible, and then 71 is prime. 83, that's probably also prime. 9 times 9 is 81. We got 41 times 2. 41, I believe, is also prime. Yep. Okay, so that's pretty much it. So we'll go back to MATLAB Cody, and we will solve a number of primes of n. So we'll say primes equals n of is prime in, and then we'll say out equals sum primes divided by length primes. Primes. There's also a different way that you can just say it, and you can just say mean primes. You can also simplify this even further by just saying output is mean of n of primes in. Go ahead and submit that. Let's see, where am I on time? Okay. So what you might want to do is go ahead. Okay, so we have I through 100. So we'll say, well, let's give the first primes equals 1, 2, 3, 5, 7. Okay, so then start equals max of primes, and then for check, it's less than of max of x. We'll just go ahead and find the primes. So let's see. So we'll say start equals start plus 2 because we know every single even number is a prime number, and then we'll say if some floor of x, or start divided by x, equals start divided by x is equal to length x, start equals start plus 2, else um, let's see, primes of, let's say, primes equals start divided by primes over length primes. Of primes of length primes plus 1 equals start. And end. It should be pretty rudimentary, pretty basic. A while there. Okay, so start divided by primes, so 9 divided by 1 is a whole number, 9 divided by 2 is a whole number. Let's see here. Doesn't equal to primes. Why did that add that there? I'm going to take 1 out of here, and then I'm going to say some primes is greater than 0. And we'll see if that gets it. Or no, we'll say if it's equal to 0, then it's prime. So we got all of our primes. Let's see, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43. Those all look like good candidates. That was pretty quick. Hmm. Hmm. I wonder if I can pilot that to see how fast I would be. Anyway, getting ahead of ourselves. Okay, so that's how you. That's essentially a pretty quick way, pretty well, maybe quick and dirty way to derive a function to find prime numbers. As you start getting into larger numbers, you would start running into floating point issues, so that's not a good method for larger numbers. Okay, well, anyway, now that we have the prime numbers, we'll say, let's see, let's see, x prime equals x of x equal to primes. And let's try that. Let's see. Let's try is member x primes. Okay. 41 and 43. Okay. And then we'll say out equals sum of x prime divided by length x prime. There's our output. Okay, anyway, I just wanted to show that whole process. The actual, like, full process, not just using MATLAB functions as a crutch all of the time. Okay, now let's go to, I think it was 15. Find the longest sequence of ones in a binary sequence. Okay, so this is a string. Okay, so the longest sequence. Okay, so what we can do, 15, find the largest set of ones in a sequence. Okay, so let's say that this equals 1. Okay, so let's say that x equals this. What we'll do is for I equals 1 to length x, we'll say counter equals 1. So what we'll say is if x of I equals to 1, while we'll say check equals 1, while check equals to 1. Let's say if x of I equals 1, sum of c, sum of c equals 1 equals sum of c plus 1, else check equals 0, and we'll break and we'll end. Yes. And x of I equals 1 plus j. I equals I plus j. Okay, so what I've effectively done here, I've said if x equals 1, then that triggers an interrupt where I say check equals 1, sum c equals 1. And I should say c equals c plus 1 here. That doesn't interrupt. Check equals 1. Sum of c equals 1, and then I say j equals 1. And then I say while check is equal to 1, so I open up a while loop. And I say if I plus j is greater than the length x, then we do break, which should end I plus j equals the length. Then we say I equals I plus j, which should exit the for loop here. Then we just break this. We also say if x plus j is 1, then sum c equals sum c plus 1. So we're essentially just counting each of these clusters. And then we say else check equals 0. Right, so if it's not 0, if it's not 1, then we say check equals 0, which breaks this. I equals I plus j, so then we start at that 0 and start checking for a 1, and then we break that. So let's try here. Let's see. Exceeds the elements. Why is that 0? So c equals 1. Whoops. Okay, now. See, that was 1, 2, 3. Okay, so that was 1, 2, 3, 4. 1, 1, 1, 1, 2, 3. So Okay, so why is that pushing it back? Okay, so we have 4, then 3. That shouldn't be a 3. What is our I at? I is at 6. So I is at 1, 2, 3, 4, 5, 6. So that should not be triggering. Okay, so I equals 6 there, J equals 4. So 1, 2, 3, 4, 5, 6. Okay, so I equals 6 here. So why does J equal? Why does J equals 4 there? Okay, so what I'm going to do is I'm just going to start here, then iterate. So they're saying I equals 2 here. Okay, check equals 0. I equals 6. J equals 4. Okay, so C equals 2. So X of I. Ah, okay. That's what's happening. Okay. So we'll say while check 1 is equal to 1, I equals I plus 1. I'll say else here, else I equals I plus 1. Let's say check 1, 1 is equal to 1, and then check I is equal to 1. And then we'll say if I is equal to length greater than length of x, then we break. Check 1 is equal to 0, and we break, and we'll end that there. Okay, let's try that. One. There we go. Okay, so the largest sum closest. What in the world? I equals 8. I equals 20. The 1, 2, 3, 4. Okay, so the fifth one. Okay, so something's going on here where x of I equals some c plus some 1. X of I plus j, 23. Okay, so then let's try x of I plus j plus 1. And 2, 3. Okay, that should get it. We'll just port that over. Then we'll say y equals sum 1. We'll call that sum 1 because that might cause issues. Sum 1 of c, sum 1 of sum 1 equal to max of sum 1. And let's run that function. Exists. Well, let's see. If c is greater than 1, else y equals 0. See what happened here. Sorry, I forgot to account for the case that they just didn't put any ones. Oh, great. Copy that back in. See what it does when I say 1. Because to me, seems to me like it should just pass 1. Y equals 0, C equals 1. Let's see. Ion time. Oh, wow. Let's see here. How can we tell if there's a sum of x equal to 1 is greater than 0? Okay. That's what we'll do. We'll say if sum of x equal to 1 is greater than 0. Try that. Oh, whoops. One equal to max of some one. There we go. That should get it. Oh, great. What's this? What's all this then? Let's add another max there. That'll solve that problem. What's this fixed? So they should be equal. So saying max of two equal numbers will just return the same number uh, instead of testing to where see if its length is greater or whatever. We'll just okay. So that concludes that. So problem 15. So we got problem 13, 14, and 15 done. So as I try to keep these around 30 minutes, and as we, you know, get up into higher stuff, it may take a little longer per problem to get these done. Even though I explain, as I go up, I'm going to explain less and do more, and it might end up taking about the same time. It's not something like just finding the maximum of an array. So anyway, it's about at the 40-minute mark, so about 8 minutes over. So I think I'll conclude that there. I hope you enjoyed it, and I'll see you later if I do.